Recording. Okay, so we talked about, or well, I guess the last couple of days, we've been talking about exponentials and logs, right? The whole idea is that we're talking about sort of measuring things in terms of multiplication, right? Or we're looking at a thing where you've got sort of a like constant growth rate or pattern, but everything's happening multiplicatively, right? So for an exponential, we're talking about taking a fixed base and raising it to a power. So the nice like counting number version of that is that you're multiplying a bunch of copies of 2 up or whatever. A logarithm is the inverse to that, right? So it's going the opposite direction. So it's sort of counting how many 2's are in a given number. So I've been talking about 2 as an example. So let's stick with that. 2 to the 4th is 16. That's the number fact, right? That same relationship, right? That same, fact as a logarithm, we would state as the log base 2 of 16 is 4, right? So what a log does is measure the exponent or find the exponent for you or tell you what power of 2 this number is, right? 16 is 2 to the 4th, so the log base 2 of 16 is 4. Maybe one more just for the sake of doing it. 3 to the 5th is, nope, it's not. Hang on. Let's go 3 to the negative 2 is 1 over 9, right? 1/9. What's that as a logarithm? The log base 3 of 1/9 is negative 2. Okay. So is everybody, sort of more or less okay with kind of the basic idea of what a log is now? I think, I'm glad you said that just now. I think you said something like log 3 or log of 3 or something like that, right? This is a place where I think being intentional, and I've been very, particular about how I said this. I think being intentional about how you say it, even when you're just like narrating it in your head, I think helps a little bit. Read it as the log base 3. I think that helps you keep in mind like what that number is doing, right? That's telling you how you're counting the thing. The base is 3. That means what we're talking about is multiplying by 3, right? Because I know that logs are a new thing, right? Probably like even if you did a couple 3 years of algebra in high school, you might not have done logs at all, or maybe just a little bit. So and that's a little different than most of the stuff that we talked about. Most of it you at least touched on before. So I know this is new, spend some time with it. Once you get this one big idea, that kind of drives the whole thing. Okay, so I gave you some homework. Y'all tell me about these real quick. First one's just an evaluation, right? You don't have to do anything. 25 is 5 squared. All right, how about number 2? There we got to actually do something. The log base 4 of x is negative 2. What does that look like if you rewrite it? Yeah, so go for it, Logan. 4 to the negative 2 is x, so x is 1 over 16. Right? Okay, how about 3? The log base 6 of 1 over 216 is x. And then evaluate the log base 6 of 1 over 216. That's negative 3, right? Yeah. This would be one that you could do by, sort of like clever guessing, right? Or just checking powers of 6. It's a reciprocal, right? 1/216, so it's going to be negative, and then 6 times 6 times 6 is 216. So like you could get it that way, or the logarithm does it for you. Yeah. Yeah, so either the change of base thing, log of the thing you wanted the log of 1/216 divided by the log of 6, we do it using just like the log button on your calculator. Or if you go to that math menu and see the log base command, you can do it that way. I can, show you if you want in a bit here. Okay, 2 to the x is 10. This one, looks kind of the same, but we can't do it by just, clever guessing because 10 is not a nice power 2, right? So how do we rewrite it then? The log base 2 of 10, that would be the exact solution, right? That's it. Or that's approximately what, 3.38? 32? That would be the approximate solution. Okay, 5. The log base 2 of x is 0. So x is 2 to the 0, which is 1. Good. All right, and then the last one, natural log, which means the base is e. So e to the 7th is x. Again, that's an exact solution. And then if a problem asks us to approximate, we'd punch e to the 7th into a calculator and get whatever that is. A lot of times on things where it's just sort of a like, here's an equation, solve it, like doesn't, not connected to any kind of context or anything. Most of the time, I'm going to be more interested in the exact solution there. Homework stuff, sometimes it'll ask you for both. And then in like applications of word problems and stuff, probably you would go ahead and get the decimal version because then you can say, oh, okay, that's 5.3 years or whatever. Okay. Do we have any questions about those? We will, spend a lot more time on solving equations next week. Basically about half of next week we'll spend on just solving equations. So for now, it's just kind of a little bit of a intro to it for the sake of this going back and forth between exponentials and logs thing. Right? There's a few in the homework for this week, but they should be not too bad. Mostly just kind of that one thing. Okay, cool. So the thing that we need to spend some time with then is what logarithms look like as functions. So for starters, let's remember what exponential functions look like. Two kinds, right? Two varieties, growth or decay, which just means the thing is either increasing or decreasing. Same shape, same domain, same range, same horizontal asymptote. Y equals 0. They've both got a y-intercept at 1. And what determines whether the thing is going to grow over time or decay over time, whether it's increasing or decreasing? missing? How do we decide if it does this or this? Like if I give you an example, y equals, I don't know, 5 to the x. Is it going to grow or is it going to decay? What's negative? The x value, okay, yeah, the x value being negative would do it, because the x value being negative would also say that really that's the reciprocal. So the base there, you could think about it as 5, or we could think about it as 1/5. Well, if you're multiplying by a fifth over and over again, do you get bigger numbers or smaller numbers? Smaller numbers. If you multiply by 5 over and over again, do you get bigger numbers or smaller numbers? Bigger. Okay, so if the base is bigger than 1, then grows over time. If the base is smaller than 1, decays over time. And again, if it, like 5 to the negative x, that looks like the base is bigger than 1, but that negative is really flipping it upside down, right? So just, sort of be aware of that. Is that, kind of caveat with it. Okay, so that's exponentials. Logarithms are the inverses to exponentials. So if you talk about a function, and notice these are 1-to-1, right? Talked a little bit about that yesterday, but they do pass a horizontal line test. If you talk about a function and its inverse, how does the inverse compare, in terms of the graph? Inverse is the opposite. So if a function takes, x over here and turns it into y over here, the inverse swaps those, right? That means graphically it turns the whole thing sideways, basically. So if we look at that's y equals 10 to the x. Base is 10, 10 is bigger than 1, so it's growing over time. It's going to be, fairly steep because compared to like 2 or something, it's going to be steeper than that, right? There's that y-intercept. The inverse to that, right, the logarithm that goes with that would be the log with base 10. So y equals log, no base, log, no base written, base 10. So there's the log base 10. That's its graph. And that's this thing with x and y swapped, right? So flipped over sideways, reflected across the line y equals x. This line stays put, everything flips over, so it turns the whole thing sideways. So what happens to the domain and the range and the asymptotes and the intercepts and all that stuff? Say it again. They're this, wait, they're not the same? Not the same as the exponential, right? But if you know the domain and the range for the exponential, you get the domain and range for the log by swapping them, right? Because x's become y's and vice versa. Okay, so the domain for this thing is the range for this, right? So this, the range is the upper half. This, the domain is the right half, right? So 0 to infinity. The domain, or the domain for this thing is everything, right? The whole real line. So the range for this is everything, right? This is pointing down, that is pointing up. It's subtle, like it takes it a long, long time to get there, but it is, heading up, right? You can, zoom or move this or whatever as long as you want. It's going to, keep kind of creeping up. The horizontal asymptote right here becomes a vertical asymptote right there. This intercept becomes that intercept, right? This y-intercept becomes that x-intercept. Okay, so if, oh, doggone it. Hang on. Sorry, I don't even have the notes pulled up here. Okay. So if the base is bigger than 1, if that's the exponential that goes with it, then the log looks like
this. And that would be true for anything where the base is greater than 1, just like for exponentials, anything where the base is greater than 1 looks like that. So there's a vertical asymptote right here. The domain is 0 to infinity. The range is negative infinity to infinity. There's a vertical asymptote now at x equals 0. And there's an intercept there at 1. Okay. And again, changing the value of the base, like comparing a base 2 or a base 10 or whatever log, you're going to get the same shape in the same place. It's just going to be a question of kind of how steep it is, right? How fast or slow it does its thing, but it's going to kind of live in the same place. All right. Flip side of that is if the base is smaller than 1. So exponential with base smaller than 1 means it's decaying, right? So decreasing over time. You take that thing and flip it over the line y equals x, right? Turn the whole thing sideways. Then what you get is something that looks like that. This is the same picture as the other logarithm, but upside down, right? The exponentials, when you go from growth to decay, you flip it this way. Well, since logs are the inverses swap x and y. For logs, you take this thing and flip it that way, right? So instead of increasing, growing over time, this is decreasing. Well, that makes sense. All the other stuff is the same, right? All of the, vital statistics stuff, this is all the same. Something like that. Vertical asymptote there, crossing at 1. All the same stuff. Okay. So log graphs are, exponential, but on their side, basically, right? Flipped over. That's it. How are, if we have like a particular base, like say the base is 2 maybe. All right, let's try sketching one of these by hand. Just to kind of get a feel for what's going to happen. Okay. Take some x values and see if we can just find a few points here. If I let x be 0, this would be the log base 2 of 0 then for the y value, right? What does the log base 2 of 0 mean now? What is that asking us to find? Think about what that would look like as an exponential, right? Base 2 raised to the, I don't know yet, equals 0, right? That would be, just rewriting this as the equivalent exponential. So 2 to what power gives you 0? There's not one, right? That doesn't have an answer. Can you take a power of a positive number and get zero? No, right? You can get close to zero. That's why exponentials do that horizontal asymptote thing. That's why they do what they do. That doesn't work, which means this doesn't work, which means that's not a thing, right? That's undefined. That's why we get that vertical asymptote here. If you're trying to think through doing that for any negative x value, the same kind of thing happens, right? How do you take a power of a positive number 2 and get a negative number back? You can't. So it doesn't live over here at all. So logs are never defined for 0 or for negative values, right? The stuff inside the log, the argument, cannot be 0, it cannot be negative. So kind of similar to what we saw with like square root stuff, right? There's a problem if you put a negative inside here or also 0. Okay, well, what about 1? What power of 2 gives you 1? 0. 1, 0. Okay. How about 2? 2 to what power is 2? It's the thing you're thinking. Yeah, 1. Or I hope it's the thing you're thinking anyway. 2, 1. Okay. 3. Ooh. 2 to what power is 3? That was not going to be pretty, right? What's the next one that is going to be pretty? When's the next time we're going to get like a nice coordinates that I can just figure out by hand? 4. Because the log base 2 of 4 is 2. This is some messy thing. I could find it. I don't want to. When's the next time we're going to get a nice point? 8. 3, right? Next one would be all the way out at 16. That's why this thing, is sort of slow, right? We talked a lot about exponentials being fast. Well, logs, you flip that on its side, you get a thing that's very slow. But it's still increasing, right? I can keep doing this forever. It's just that the next time I get to again, like a nice point would be 16.4, right? 32.5 would be like the next one. So you're going a really long way out that way to go, up 1 in terms of the y value, but like it keeps going, right? Keep doing it. If the base was 3 instead of 2, what would the nice points that I could do by hand look like? Like what would they pass through? Well, here the base is 2 and they go through the powers of 2, right? 2, 4, 8, 16, those are the places that you're going to get nice points. Well, if the base is 3, you get nice points at powers of 3. Right? So 1, 3, 9, 27. Those would be, sort of the nice ones, right? Just like on an exponential, the nice points are y values are powers of the base. Here, the x values are powers of the base because again, it's the inverse, right? So you swap x and y. Everybody sort of okay with that? Yeah. Okay. All right. Transformation stuff works the same way it always has. So if we looked at like number 1 here, log base 2 of x minus 1, what does that minus 1 do? Shifts it down because it's outside of the logarithm, right? So we're going to take a thing that looks like this and has coordinates at points that we just found, right? We just did a bunch of them for the log base 2. We're going to take that and shift it down more. So now instead of crossing the x-axis at 1, go back to my other graph I already drew and break everything somehow. I'm just standing here. Like, I don't know what okay. If everything got shifted down 1, right? So take 1 away from all the y coordinates, this would be 1, -1, 2, 0, 4, 1, right? Just push the whole thing down 1. Does the vertical asymptote move? No, because you moved it down, right? If you moved it left or right, then it would move along with everything else, but you moved it down. Does the domain change? Take a thing that's restricted like this and move it down, domain doesn't change. What about the range? No, I mean, maybe, because we're moving it down, we're moving it in the y direction, but the range was everything. If you move everything down, it's still everything, right? About infinity -1. X-intercepts 2. Y-intercept still no. And the vertical asymptote is still x = 0. Somewhere out here, I'd go through 4, 1, right? Okay, the other one, number 2 there is similar. What's that x + 3 going to do? Shift the whole thing to the left because it's inside the parentheses, right? It's inside the log, so it's going to take everything and shift it to the left, 3. Okay, start with the vertical asymptote because that's a good reference point. Shift that to the left 3. Everything else shifts to the left 3 along with it, so that's going to change domain. It's going to move some of the asymptotes or the asymptote and some of the intercepts and stuff around. But again, it's just doing the translation the same way it always has. These are in exponentials too. They're not as visually distinct as some of the other stuff, right? Like just looking at the shape of the thing, it's not like a quadratic where you've got a point that you can definitely identify, visually. Like this thing, once you start moving it around, it's hard to tell this point from that one, whatever. So the asymptote is a good reference. And then just, if you need to, keeping track of a point or two is a good way to do it as well. On something like a test question, things to look for, things that I'm going to be, kind of trying to communicate is that if you know the base, then you can figure out, sort of what's going on by looking at, powers of, right? So if I see a thing that hits 1 and 3 and 9 and 27, okay, the base must be 3. If I see a thing that hits 1 and 2 and 4 and 8, well, okay, the base is 2, right? So, sort of using that to figure out what's going on. Okay. Anybody have a chin? McKinley, I know you emailed me about the graphing thing in my math lab. Was it the using the actual thing that's in there, or? Yeah. Okay. So it's the same kind of thing. Once you tell it that you want, let's see this. Once you tell it that you want a exponential graph or a log graph, it's going to pop up this little box and have you type in what you want it to do, right? So if you're none of them should have any stretching stuff going on. It should just be shifting left, right, or up and down. Just type in I want it to move down. Just type in or -2, and then make sure that you set the base also to match. So here, I would just tell it that I want the base to be 2 and I want the shift to be -1 vertical, right? Okay, so the other thing to talk about here is just how we make sense of what the domain of these things are, right? So if we can kind of look at it and identify the shift that's happening, right? Like the parent function here would be the log base 2 of x, and its domain is 0 to infinity. Well, what does this do? It's +3. It's inside the logarithm, so it's going to be horizontal. +3 would shift it 3 to the left. Okay, well, if you take this and shift it 3 to the left, what's the domain? -3 to infinity, right? Instead of 0 being where that asymptote occurs, right? And it is, you know, an asymptote in the same sense as other stuff. Like you can get as close to that as you want, but you can't actually hit 0. If that's at 0, we shift everything 3 to the left, well, that puts it here, right? Okay. Another way that we could look at that is that what a logger or the way a logarithm works is that it's telling you how many 2's or what power of 2 this thing is. Well, because the base 2 is a positive number and it's always going to be a positive number, this thing can be anything that's positive. It cannot be 0. It cannot be a negative number. So if I wanted to figure out the domain without, you know, relying on looking at a graph, because that's a little bit hard to read sometimes because the shape of the thing is kind of, you know, amorphous. Like you don't have as good a reference point for the shape of the thing graphically. And if there's too much going on for me to figure out what the transformation is, right? If I can just see that it's 3 to the left, well, okay, fine. If we can't though, the important thing here is that that's got to be positive. So figure out where it's positive. X plus 3 is greater than 0 when x is greater than -3. So the domain is all the x values that are bigger than -3. Right? If -3 is there, this is fine, this is not. So it's -3 to infinity. So we can do the domain here, you know, similar to what we did with the radical function stuff. Come back to that in a minute. We can do it by looking at, okay, it's a logarithm. For a logarithm, it's only going to be defined if the stuff you're taking the log of is positive, so figure out where it's positive. So something like, you know, maybe number 6. If I'm trying to find the domain here, this is kind of enough going on that, you know, just figuring it out in terms of transformations is going to be weird. There's a shift. There's a reflection, there's a stretch thing happening. Those kind of affect each other. So the shift is actually 2 instead of 6. Like it all gets a little bit weird to break all that out. But I can get the same information by saying, okay, well, whatever this thing is, I know it can't be negative. So figure out where it's not negative. And there we go. That means if I'm looking at, you know, this thing on a number line or the x-axis, what I should see is that vertical asymptote is going to happen at 2. That's where that's, you know, been shifted to. And stuff over here is going to be okay, and stuff over here is not going to work. So the domain is -infinity to 2. This would be parentheses at 2 because that's where that vertical asymptote happens. Plugging into would give you the log of 0. Log of 0 is not defined. Okay. So we're adding a thing to the, you know, list of things where we need to worry about domain, right? Rational stuff because you can't divide by 0. Square roots or even roots really because you can't take the square root of a negative number. Logs because you can't do the log of 0 or a negative number, right? So that's our list of, you know, places where we got to think about domain and you know what can happen. Okay, so I'm going to leave the rest of those for y'all for homework. Does anybody have any questions about things at this point?